Hey guys, Miss Peterson here, and welcome to Notes 1-3, which is just going to be our Stoichiometry 101 notes. This is something that you probably have some idea about from prior chemistry classes, but I think it is always good to go back over it and review it some more. Okay, so first I want to work on us just kind of conceptualizing stoichiometry, and we're going to do that with a sandwich example. Okay. In order to make one sandwich, I need 2 pieces of bread and 3 slices of turkey. We have a very boring sandwich, but that's what's on it. Okay? So if I was going to write that reaction, I would say 2 bread plus 3 turkey equals 1 sandwich. Okay? And just like in chemistry, we don't write the 1s as coefficients, so I'm not going to write the 1 there. Let's go ahead and abbreviate these so that we can do that. I'll use B for bread, TU for turkey, and we'll do SA for sandwiches so that it looks a little bit more like a chemical reaction. Okay, so how many sandwiches can I make with 1.5 loaves of bread and 2 packages of turkey? Well, I know how many pieces of bread I need, but I don't know how many loaves. Okay, so I went to Google, just like in stoichiometry, you would go to your periodic table, and I found out that 1 loaf of bread is about 16 slices. Okay, and 1 package of turkey normally contains about 32 pieces of turkey. Okay. So we're going to use these as our conversion factors in a similar way that we would do like molar mass or something. Okay, I need to figure out which one of those limits how many sandwiches I can make. So with this, it should be pretty clear to see. With 16 slices of bread, and then I know that I need 2 slices, okay, for each, oh wait, I have 1.5 loaves of bread. So 1.5 loaves. And then I can convert that. Every 1 loaf has 16 slices. Okay, so that gives me, yes, I'm plugging that into my calculator, don't make fun of me, 24 slices, which I can do some simple math, okay, because it's that 2-to-1 ratio, and I know that 1.5 loaves of bread can make 12 sandwiches. Okay, slices is what it's written. I'm basically going, hey, I need 2 slices per each 1 sandwich. Okay, let's do the same thing with the turkey. Okay, if I have 2 packages of turkey, okay, I said that 1 package is 32 pieces, and then I know I need 3 pieces. Or actually, let's go ahead and stop there so I can show you guys this and make it line up with the other one. So 64 pieces of turkey. And then I need 3 pieces to make 1 sandwich. And so with this, I can make 21 sandwiches. So when finding the limiting reactant, you're basically saying, what will you run out of first? So I'll start making my sandwiches, and which one am I going to run out of first? Well, I'm going to run out of bread. I only have enough bread to make 12 sandwiches, okay? And that only needs, let's see, 12 times 3. That only needs 12 times, come on, 36 pieces of turkey, and I have plenty of turkey for that. So my turkey's going to be in excess, and my bread is going to be my limiting reactant. Okay, so this is my limiting reactant. And I could see how many pieces of turkey I would have left over, and I will make 12 sandwiches. Okay, cool. Okay, cool. So there are a couple of different types of stoichiometry conversion factors that we use. Okay, these are analogous to the loaves of bread and the pieces of turkey in a package. We use molar mass, that's when converting from grams to moles. Our list of molar masses is the periodic table. We use mole ratios, which is the ratio of two different substances. For example, 2 red to 3 turkey, or 1 oxygen gas to 2 hydrogen, things like that. Liters of a gas we'll talk about more when we get to our gases unit. And then if I want to talk about particular particles, I would use Avogadro's number. Okay, how many actual number of atoms and molecules and particles do I need? Okay, so let's do some example problems. Determine which of the following samples contains the fewest sodium atoms. Okay, so I have 1 mole of sodium oxide, 45 grams of sodium fluoride, 50 grams of sodium chloride, 1 mole of sodium nitrate. Okay, well that is a lot of chemical formulas, so I'm going to need to figure out what all of those are first. So let's do a naming review and ionic compound review. Sodium's a metal, oxygen, fluorine, chlorine, and nitrate are all nonmetals and a polyatomic, so we can figure this out. Okay, sodium has 1 valence electron. It will lose that one and become an Na+. Oxygen has 6 valence electrons because it's in group 6 on the periodic table. So it will be O2-. So in order to get those to bond and the charges to balance, the formula of sodium oxide is Na2, Na2O. Okay? Now what that means, for every 1 mole of sodium oxide, I have 2 moles of sodium atoms, because there's 2 sodiums for every 1 sodium oxide. Now I'll switch to another color for the next one. Okay, we got sodium fluoride. Fluoride is F-. Okay, so Na and F, the formula of that one is just going to be NaF. But this time it's giving me my grams. So in order for me to compare, I need them all to be in the same units. And because moles is what we use to count atoms normally, I'm going to go ahead and just convert the grams to moles. So 45 grams, I need to find the molar mass of sodium fluoride, okay, which is 22.99 plus 19.00. Okay, so the molar mass of sodium fluoride is 41.99 grams per mole. Okay, so 45 divided by 41.99, I have 1.07 moles of sodium fluoride. Okay, now that is a 1-to-1 ratio. 1 mole of sodium fluoride means 1 mole of sodium. So I have 1.07 moles of sodium atoms in B. Now let's analyze C. We have sodium chloride. Chloride is Cl minus. You probably know that sodium chloride is NaCl. And its molar mass is 58.44 grams per mole. Okay, and I have 50 grams of it. So I have 50 divided by 58.44, 0.85 moles of sodium there. Okay, moles of sodium chloride, which is going to equal my moles of sodium. 0.855, so I'm just going to say 86. Okay, and last one, let's go ahead and analyze. We have nitrate. Nitrate is a polyatomic. It is NO3 minus. Sorry, no secret there. You just got to memorize those polyatomics. So if I have sodium nitrate, that is just going to be NaNO3, because it's a 1 plus and a 1 minus, 1 minus 1 plus. So if I have 1 mole of sodium nitrate, that's going to be 1 mole of sodium. Okay, so the fewest sodium atoms would be the 50 grams of sodium chloride, because that is the only one that is less than 1 mole of sodium. Okay, and if you didn't have a calculator, you could probably still solve this out. You would just have to find those molar masses, and you would be able to see, okay, this one is a little less than a mole, this one's a little more than a mole. Okay, now Let's do the second one. Without using a calculator, arrange these samples in order of increasing number of oxygen atoms. 1 mole H2O. That one is then going to be, I'll keep it in the same order, 1 mole of oxygen, 1 mole of CO2, that's going to be 2 moles of oxygen atoms, 42 liters. Okay, so this one, like I said, we haven't talked about it that much yet, but there's 22.4 liters per mole when you're talking about a gas. So 42, that's going to be slightly less than 2 moles of O2. Okay, oxygen gas is O2. So if that is slightly less than 4 moles of slightly less than 2 moles of O2, that's going to be slightly less than 4 moles of oxygen atoms. Okay? Now, if I have 4.23 times 10 to the 23rd molecules of O3, okay, well, we know Avogadro's number is 6 times 10 to the 23rd. So this is about half a mole of O3, but then we have 3 moles of oxygen for each of that. So this is approximately 1.5 moles of oxygen atoms. Okay, so in order of increasing number, the least is going to be 1 mole of H2O. Then we have the 1.5, 3 times 10 to the 23rd molecules of O3, which is going to be less than the 1 mole of CO2, which is 2 moles of oxygen atoms. And the one that has the most is the 42 liters of oxygen gas. Okay, cool. Okay, cool. Last one. How many moles of water are in 1 liter of water, whose density is 1 gram per milliliter? So this one, we're just going to set up a big old conversion problem. Okay, if we start with our known 1.00 liters of water, first I'm going to convert it to grams, okay, because I know I can get from grams to moles using the molar mass, but first I have to be in grams, okay, and I know that it is 1 gram per milliliter, so I need to convert from liters to milliliters. You guys should know that 1 liter is the same as 1,000 milliliters. Then we can use its density. If I have 1 milliliter, I have 1.00 grams. You could have also combined these and seen, okay, well, if it's 1 gram per milliliter, it's going to be 1,000 grams per 1 liter, and you could have done that as well. And then we need the molar mass of water. The molar mass of water is 18.02 grams per mole. So 18.02 grams is 1 mole. Okay? And you guys can see how those units work out. 1 liter of water is 1,000 milliliters. Okay, 1 liter, 1,000 milliliters, that is true. Milliliter and milliliter cancel out. 1 milliliter is 1 grams. Yes, that is true. That cancels out. And then 18.02 grams is 1 mole. So we're good to go there. The units that we're left with is moles, which is good because that's what we were looking for. And we basically have 1,000 divided by 18.02. 1,000 divided by 18.02. And we get our answer of 55.5 moles of water. Okay, cool. Okay, cool. Let's do some stoichiometry problems. We're going to do that, and then we're going to do 2 stoichiometry problems, and then some limiting reactant problems. Right? And they do kind of all blend together. I'm sorry. I should have put it just like on top, and these are just practice problems that we're going through. Okay, so the decomposition of KClO3 is sometimes used to prepare small amounts of oxygen gas in the laboratory. How many grams of oxygen gas can be prepared from 4.50 grams of KClO3? Okay, so 2 moles of KClO3 dissolves to form 2 moles of KCl and 3 moles of oxygen gas. Okay, chemical reactions are written in terms of moles. So step number 1 and the last step are always going to be to convert from moles to grams or from grams to moles. Okay, which means grams to moles, molar mass. Grams to moles, molar mass. Grams to moles, molar mass. We need to find the molar masses of our substances. So let's go ahead and do that. Okay, KClO3, I have a potassium. I'm just going to do this all in my calculator, but I'll explain what I'm doing as I'm doing it. So we have a potassium atom, which is 39.10, plus a chlorine atom, 35.45, plus 3 oxygens, so 16.00 times 3. Okay, so the molar mass of KClO3 is 122.55 grams per mole. Okay, and then O2 is just 2 oxygen atoms. It's 16 each, so 32.00 grams per mole. And now we're ready to convert and do our stoichiometry. So 4.50 grams of KClO3. Now, if I had 122.55 grams, that would be 1 mole of that KClO3. Okay, so that's the step to convert it to moles. For every 2 moles of KClO3 that decompose, I get 3 moles of oxygen gas, which makes sense. 6 oxygen atoms, 6 oxygen atoms. It's a balanced reaction. If I solved it out right now, I would know how many moles of O2 I could prepare, but it asked for grams. So last conversion factor is just to convert it back to grams. So 1 mole of O2 is 32 grams of O2. Okay. When doing these type, I highly recommend, I don't recommend, you have to write the chemical formulas as a part of your units so they don't get mixed up. And it also allows you to show your work for that really cleanly. So AP readers, when they're reading your tests, can very clearly see those ratios. So grams of KClO3 cancel out, moles of KClO3, moles of O2. I'm left with grams of O2. And then I plug it all into my calculator. 4.50 times 3 times 32 divided by 122.55 and 2. And I get 1.76 grams of oxygen gas. Okay, cool. Okay, cool. Okay, so the most important commercial process for converting N2 from the air into nitrogen-containing compounds is based on the reaction of N2 and H2, nitrogen gas and hydrogen gas, to form ammonia, NH3. How many moles of NH3 can be formed from 3 moles of N2 and 6 moles of H2? Okay, so if we look at this reaction, N2 plus 3 H2 goes to N2 NH3. Okay, so it is a 1 to 3 ratio. For every 1 mole of nitrogen, I need 3 moles of hydrogen. So if I had 3 moles of nitrogen, I would need 9 moles of H2. And I don't have 9 moles of H2. I only have 6. Okay? So if I have 6 moles of H2, for every 3 moles of H2, I get 2 moles of NH3, 2 moles of ammonia, because it's that 2 or 3 to 2 ratio. So I have 12 divided by 3, I would get 4 moles of NH3. And if you're ever in doubt, you can solve it out for the other one. Say I used my 3 moles of N2, and I figured out how much product I would form. Well, every 1 mole of N2 forms 2 moles of NH3, so that would give me 6 moles of ammonia. But I don't have enough hydrogen to form that 6 moles of ammonia. I just don't have enough hydrogen atoms. So this is our answer, and the hydrogen is our limiting reactant. Okay, cool. Next problem, here we go. Molten gallium, ooh, fun, reacts with arsenic to form the semiconductor gallium arsenide used in light-emitting diodes in solar cells, okay, LEDs. If 4 grams of gallium is reacted with 5.50 grams of arsenic, how many grams of the excess reactant are left at the end of the reaction? Okay, so this is a super challenging problem, but let's go ahead and solve it out. We got this. So, step 1, we know we're going to need our molar masses. Let's just look them up real quick right now. Okay, so gallium, you find it on the periodic table. It is atomic number 31, and it has a molar mass of 69.72 grams per mole. Where arsenic is number 33, and it has a molar mass of 74.92 grams per mole. Okay, and it's only asking us for the excess reactant left at the end, so we really don't even need to worry about the product. We're not given it, we're not asked about it, so we don't even need to find its molar mass. Okay, but what we do need to find is we need to find which one of these we have more moles of. When it's a 1-to-1 ratio, it makes it a little bit easier to compare, so we just need to convert to moles. So, if we have 4.00 grams of gallium, okay, we have 69.72 grams of gallium is 1 mole of gallium. So, okay, that means we have 0.057 moles of gallium. Let's do the same thing for arsenic. 5.50 grams of arsenic. Okay, the grams are pretty close and the molar masses are pretty close, so you might not be able to see immediately which one you actually have less moles of. Unless you have a very math brain that can see those ratios really cleanly. I wish I did, but I do not. Okay, so 0.0734 moles of arsenic. Okay, and I just realized I cut a sig fig off of the first one, so let me write that down. 737, so there should be a 4 at the end. Okay, so because they react in a 1-to-1 ratio, whichever one I have less of is going to be my limiting reactant. Okay, so this guy is going to be my limiting reactant. Okay, now, like I said, it's a 1-to-1 ratio, so that makes it super easy for us. Okay, that means that this needs 0.0574 moles of arsenic in order to react completely. Okay, if you have this much of this, you need this much of this. This is how many moles I have. So I'm just going to convert it from here. I could also convert this to grams and then subtract grams by grams, or I can subtract mole to mole and then convert. Because I already have both of these numbers written, that's what I'm going to do because I think it's a little easier. So that's how many moles I have, and then I'm going to subtract how many I need in order to complete that reaction. And I get 0.016 moles of arsenic. And then the last step, we just have to convert it back to molar mass. So there's how many grams per mole it is. I plug it into my calculator, and I get 1.198, so about 1.20 grams. Answer option A. Okay, cool. Okay, cool. Last problem. Okay. When a 2.00 gram strip of zinc metal, okay, so 2.00 grams of zinc metal is placed in an aqueous solution, so it's just placed in a solution with 2.50 grams of silver nitrate, they give us the reaction. We're going to ask what is limiting, how many grams will form, how many grams of the other one will form, and how many grams of excess are left at the end. Okay, so Let's find our molar masses because we know we're going to need them. Zinc is number 30 on the periodic table with a molar mass of 65.38 grams per mole. And then silver nitrate, we have a silver, where's silver? 107.87 plus nitrogen, 14.01 plus oxygen, 16.00 times 3 oxygens. So that one has a molar mass of 169.88 grams per mole. Okay, we're going to go ahead and write in the rest of them too. Silver is 107.87 grams per mole. And then zinc nitrate, zinc 2 nitrate, 65.38. Plus I have 2 nitrogens, so whenever you have something outside the parentheses, you got to distribute it in. So 14.01 times 2 plus 16.00 times 6. And we get the molar mass of 189.40 grams per mole. Okay, so now we need to figure out which is limiting. Again, it is not that easy to see because we have about equal masses, and then we need twice as much silver nitrate, but it has a much higher molar mass. So, okay, if I need twice as much of it, and I have a little bit more, but less moles, will it be the limiting or will it be in excess? Maybe you just need to calculate it out. Let's calculate it out and find out. So if we have 2.00 grams, I'm going to zoom in a little bit farther so you guys can see this. Okay, we have 65.38 grams of that is 1 mole of zinc. So we have 0.0306 moles of zinc. Okay, do the same thing for the silver nitrate. Okay, 2.50 grams of the silver nitrate. 169.88 grams is 1 mole of the silver nitrate. And we have 0.0147. Okay, so moles of the silver nitrate. Okay, now I know that I need twice as much silver nitrate as I need moles of zinc, but I actually have like twice as much zinc as I have silver nitrate. Okay, so which one's going to be my limiting reactant? Okay, which one am I going to run out of first? I'm going to run out of the silver nitrate way before I run out of the zinc. Okay, so the silver nitrate is my limiting one. 1, I have less of it, and 2, I need more of it because of that 1:2 ratio. Okay, so that's going to be the one that's going to limit the formation of my product. So I'm going to go ahead and find out how many grams of silver will form. This is just a conversion problem, starting from my limiting reactant. Actually, I'm just going to start from my moles because I already calculated it out, and it'll be one less step then. So if that many moles of silver nitrate react, for every 2 moles of silver nitrate, I get 2 moles of silver, okay, showing that mole ratio. And 1 mole of silver has a mass of 107.87 grams. Okay, so 0.0147 times 107.87 times 2/2, 1. And so I will get 1.59 grams of silver. Okay. Go ahead and do the same thing with the zinc nitrate. 0.0147 moles of our limiting reactant. Okay, for every 2 moles of our silver nitrate that react, I get 1 mole of zinc nitrate. Okay, which makes sense, 2 nitrates, that's how this works. 1 mole of zinc nitrate has a mass of 189.40 grams. Okay, and so now we plug that all into our calculator. And we get 1.392, so 1.39 grams of the zinc nitrate. Okay, cool. Okay, cool. If you tried to solve it out using your other reactant, you would actually get a much higher number. And that is a way that you could check. So, for example, if I were to solve out this, but instead using my zinc, okay, so I would have 0.0306 moles of zinc, okay, and then that is a 1 mole of zinc gives me 2 moles of silver, and then the last step is just this one. I'm just going to show you really small here, so times 2 times 107.87, and I get 6.60 grams. That is much higher than what I was actually able to form. So, you know, just another way that you can kind of check your answers. So how many grams of the excess reactant are left at the end? Okay, well, let's go ahead and figure out how many will react first. Okay, so in order for actually, I'm going to do it in one step so you guys can kind of see how that works. We're going to start with how many grams we have. Okay, we have 2.00 grams of zinc. And then we need to subtract the grams that will react. Okay, so I know that I have 0.0147 moles of the silver nitrate. Okay, and then for every 2 moles of silver nitrate, I need 1 mole of zinc. Okay, that would give me my moles of zinc, but I need to subtract it from the grams. So 1 mole of zinc has a mass of 65.38 grams. Okay, aka I'm doing this, dividing it by 2 to know that I need 0.00735 moles of zinc. Okay, I could just subtract that from the 0.0306 up here and solve it out that way. If I multiply it by its molar mass, 65.38, that gives me that this whole term, the amount of zinc that will react is 0.481 grams of zinc that will react. Okay, so then I just have to subtract it, 2.00 minus that answer, and we get our final answer of 1.52 grams of zinc left over, or in excess. Okay. Okay, cool. Okay, cool.